Hi, in this lesson we are going to review some of the basic skills required to be successful not only in physics class but also in any science class. My hope in going over some of this material is that it will be a review to you, jog your memory on your previous learning of this material, and to help you get started in this school year. Let's get started. Science is often concerned with the measurement of physical quantities. Okay, for example, measuring length or electric charge or time. Now, when we measure these quantities, we have to decide on a unit with which to measure them. In other words, we want to be able to agree within a classroom, within a country, ideally within the world, that we're all going to measure this particular quantity using this particular unit. For example, if I'm measuring the diameter of the CD, okay, typically the established unit of length for measuring the length of an object is the meter. Right? Now you could also use inches or feet. Those are other established measures, but in the metric system we use the meter. In this case, okay, we would express the diameter of the CD as 12 centimeters or 0.12 meters. Now I should point out here that we could use your foot, right? We could use your foot as the established unit of length, right? We could say this football field is 335 Johnny's feet long, right? We could do that as long as everybody agreed on it. It's just that we agreed on the meter, okay? Now, the units that we have chosen, we want them to be defined in such a way that everybody can access them. So take a look at the definition of the meter, okay? It's defined as how far light travels in a certain period of time, in a very small period of time, right? It's an extremely small period of time. The kilogram is a little bit different. It's unique in that we have an actual kilogram that exists. Okay, I believe it's kept in Paris and it's an actual artifact. The second, okay, is defined as some aspect of the behavior of cesium atoms. Okay, in other words, again, something that's very universal, something very basic to the universe. So these are units that we've agreed upon. The way to measure time, the way to measure mass, the way to measure length. Here is a list of the 7 fundamental units. Okay, these are the 7 fundamental measurements that you would make. And you see their associated units and symbols. There is more than one established set of units. Okay, you can see on the next page here. Okay, the SI system. SI is a French term for the metric system. Okay, basically we call the SI system the metric system. And then there's also the USCU, which we refer to often as the English system, right? You know these units in more familiar terms. If I go to this table here, okay, for example, mass. Actually, you're probably not familiar with the slug, but if you look at force, right, the metric unit is Newton and the English unit is pound, right? You're used to measuring your weight in pounds, not newtons. But in Europe, they use newtons. When you make measurements, a measurement can be good in 2 different ways. You see the words here, accurate or precise. We use these words interchangeably, but actually in scientific terms, they are related but not the same thing. Okay, here's how we define accuracy. Say you happen to know the true value of a measurement, right? You happen to know exactly how long. The closer that your measurement is to that actual length, right, that true length, that would be the accuracy of your measurement. Let's look at precision. Precision is different, okay? Precision indicates how closely together your measurements are lumped. So if you make 10 measurements and they're all really close together, right, they're all very close to the same measurement, we could say that your measurements are precise, okay? And again, we'll get to this about random error a little bit later. So let me give you a visual between precision and accuracy. Let's focus on the 2 bottom examples, okay? If you look at the bottom left here, right, if you look at this set of shots, okay, you can see that they're clumped really close together, right? Now they've missed the target, but they're clumped really close together. Okay, for example, if you were trying to evaluate how good of a marksman somebody was with a gun, you would actually say that this person is a pretty good marksman, okay, because all of their shots are really close together. Now, they missed the mark for some reason, right? Maybe something on their scope or their guide on their gun was off, right? But when they shoot, they really hit the same spot every time. So there's value in being precise. Obviously, you know, in an ideal world, you would be both precise and accurate, right? You hit the target and you hit it in a very close together clump, okay? So this is a good picture down here at the bottom of the difference between precision and accuracy, okay? I can highlight this for you in another way with another visual, which I'm going to do to the side of this picture. All right, let's draw a number scale, okay, like this. All right, and this is low, like 0, and this is 10. And let's just say, for the sake of clarity, that this right here is the true measure of what you're trying to measure, right? Right at 5.0. If you make a series of measurements, right, and you measure the length to be all right here, right, all like this, all clumped together like this, okay? Would that be considered precise, accurate, or both? That would be considered precise, right? Because they're all clumped together, but you've clearly missed the target, right? So that would be like the lower left. They're all clumped together, but you've missed the true value. So we would say that this particular set of measurements is precise, but not accurate. Another topic to consider when making measurements of physical quantities is significant digits. Okay, so let's look at some examples here. All right, remember that some digits are considered significant, some are not. So in the case of a decimal, right, the zeros before the numbers, the non-zero numbers start, are not considered significant, right? So we only consider the 6 and the 2 significant. This one actually has 5 significant digits. So when the zeros come after the numbers have already started, right? So here's the decimal. This is significant, significant, and now you're saying, look, those 2 zeros mean that you're very precise. You can say, like, to the 10,000ths of a centimeter, I know that this is a 0, right? If you're not comfortable with sig figs, you're going to want to write these down so that you can look them over on your own time. But I would expect this to be reviewed. If you are comfortable with this, you can just move on to the next screen. When we combine with sig figs, we have to follow some rules, and there's one rule for multiplication division, and there's another rule for subtraction and addition. So let's look at the first rule here, okay, for multiplication division, right? So when you get your final answer, right, what we're trying to get you to do is not be a robot and just copy what's on the calculator screen. You have to go back and say, how many sig figs am I justified in carrying? Well, in this case, you go with the number, right? And you're multiplying, you're dividing, you go with the amount that is in the number with the least number of sig figs, right? So this has 3 sig figs, this has 4 sig figs, and this only has 2 sig figs. So that's why we end up crossing out and going with 6.9 as our answer, only 2 sig figs. You can see we ended up with 7.0, and that's because that 9 had to be rounded up because of the 7 after it, so we end up with 7.0. The second rule concerns when you are adding and subtracting, okay? The rules are similar, but slightly different from multiplication and division. Again, let's take a look at an example. All right, so we're adding some numbers here. Notice that the numbers have different numbers of sig figs. You might want to ask yourself how many there are. How many are there in this first one here? That's right, 3 sig figs, okay, 2 sig figs, and 3 sig figs. And then we end up with an answer with 4 sig figs, okay? Again, we don't want to be the robot and just say, hey, the calculator has 4 sig figs, I'm going to record that. We want to pay attention to how much precision we're allowed to have. So if you look at the rule here, okay, the least precise measure, right? Least precise means the one with the least number of decimal places, okay? So we have to go with the 10th place, all right? So the way we're going to express our final answer here, okay, is not what the calculator says, but we're going to make the final answer match the decimal place of the one with the least number of decimal places. Okay, we're going to write it like this, all right? So notice that in this case, right, it's slightly different from the multiplication division one because we still end up with 3 sig figs in our answer, right? If this were multiplication division, we can only have 2 sig figs because the number with the least number of sig figs is 2 sig figs. But that's not what we do when we add and subtract. We look at the decimal place. So since the decimal place was to the tenths for the one with the least precision, 8.4, we go to the tenths with our final answer when we add and subtract. Okay, our final topic is another one that should be familiar to you, and that is scientific notation, the way to make really big numbers and really small numbers more readable and more practical to record. So here we have some really small numbers and some really big numbers, and you can see that when we use the power of 10, we can get much more compact ways of writing them. All right, here's some examples, right? 93 million miles happens to be the distance between the Earth and the Sun. Okay, we can write that with a lot less digits, right? Some other examples. You just have to decide when you go from the number itself to scientific notation if you move the decimal to the right or to the left. Let's look at an example on the next page here. In this example, and again, we can practice what we learned previously. How many sig figs here? That's correct, 4 sig figs. Okay, 4 sig figs. Now, it's asking us to express this in terms of only 3 sig figs. So we're going to do scientific notation. We're going to do the first part, okay, which is called the mantissa, right? That's the 3.24, the 1.67. This is typically going to be a number between 1 and 10. Notice how that happens, 6.80, okay, that's 3 sig figs. And the way that we did that is we took the decimal place and we moved it until we got to a number between 1 and 10, right? So if I put the decimal place right there, I get 6.798, and then I need to round that to 3 digits, which becomes 6.79, but that 9 rounds up because the 8 after it bumps it up, so we end up with 6.80. That last 0, that says something, right? It says it's better than 6.8. 6.8 just means 2 digits of accuracy. 6.80 is that one last digit of precision. That's it for scientific notation. I hope that these subtopics, scientific notation, significant figures, basic unit measurement, were a review, and that precision and accuracy is more clear to you.